4.4 is evaluating logarithms and the change of base theorem. A couple important logarithms. The common log has a base of 10. The common log has its own notation, which is just log. So if you don't write a base, you are saying that the base you are working with is base 10. Natural log has e as a base, so log base e of x is ln of x. I try to write my ln, I write that in cursive so we don't mistake that for an I, capital I-N, but the notation is ln of x. So those are some important bases. We have the change of base theorem. So if let's say that base A is not favorable to us for some reason, we could choose to change the base and choose a new base, such as common log or natural log, and rewrite the logarithm in a base that we would prefer. So the change of base theorem is that you pick the new base, so log of whatever new base you pick, and then the argument in the numerator, the logarithm in the numerator, is the argument of the original. Now we choose the new base, and the original base is the argument in the logarithm that is in the denominator. Do not confuse this for the quotient rule for logarithms. So for example, let's write log base 2 of 11 using common log. So if I have log base 2 of 11, that is log 11 over log 2. Now remember, just writing log means base 10. So we had chosen base 10. And then natural log is base e. So log base 2 of 11 is the same thing as saying the natural log of 11 over the natural log of 2. Let's just do a part C here. Let's just write that in base 5. So we can actually see the base rather than common log or natural log. We'll put base 5 here. So log base 2 of 11 is equal to log base 5 of 11 divided by log base 5 of 2. And this section is going to have you get familiar with your calculator, evaluating logarithms by typing some stuff into your calculator. Every calculator model is different. I've got this one just sitting right here. I don't think I need to waste your time punching buttons into this calculator. So just make sure you're familiar and able to do logarithms and approximate them in your calculator if we need to. So we're going to take a look at a couple applications. Applications of logarithms are immense. I picked one out of the book that you guys might run into in chemistry. The pH calculation is negative log and then the hydronium ion concentration. So this gives us the pH scale, just in case we need to recall. 1 on the pH scale is very acidic, 14 on the pH scale is alkaline, and then 7 is neutral. So an example would be to find the pH when your H3O is 6.3 times 10 to the negative 5th. So in the pH formula, I've got negative log, now that is common log, 6.3, and then times 10 to the negative 5th. So what we would want to do to make this an easier calculation is use the product rule. So negative log, so I'm going to put the negative on the outside, and I'm going to use the product rule because log of 6.3 times 10 to the 5th can split into 2 logs. So this is the product rule for logarithms. And now we can use the power rule for logarithms, so this -5 can be the coefficient. It's the exponent in the argument, which the power rule allows us to move that to the coefficient. So the common log of 10 is 1, and that comes from log base A of A equals 1. So the base is 10, the argument is 10, and if you recall, that is because A equals A to the first. If we were to transform that to an exponential equation, it's pretty easy to see A equals A. So this is going to be 1, so we have negative, keeping my parentheses straight here, -5, and if we just wanted to distribute that at this point, so it would be useful to have the approximation here, so that's why I brought this along. About 4.2 is the pH. For this value for the hydronium ion concentration. Okay, if you guys have ever heard of, maybe a child and they say like when they're growing they're in the 90th percentile or something like that, that is actually a logarithmic curve. So I just took a function with the logarithm, and we're going to examine a certain species, the length as it ages. Generally growth curves are logarithmic. It'd be kind of strange if an animal size grew exponentially. We'd have some pretty large dogs, I guess. But as you know, as we get older, we tend to stop growing in height and things like that, but when you're young, so that is generally a logarithmic model. So I just made this, made this function up. So we're just saying some certain species we've determined, the growth curve can be modeled by 2 natural log and then x plus 1.5 in the argument of the natural log. So we have x is time in years, it's the independent variable, and f of x is the overall length in feet. So what is the length at birth? So we would do f of 0 equals 2 times the ln of 0 plus 1.5, and type that into the calculator. It's about 0.8, and we are using feet in this particular example. And then at what age is the animal 3.75 feet? So we want the output of the function to be 3.75. So we're going to replace f of x with the desired output of 3.75. And we're going to end up with a little bit of an equation here to solve. So if we have the natural log of x plus 1.5, we would exponentiate both sides using base e to cancel out that natural log. So we would take the exponential of both sides. Now, if we have a to the log base a of x, that just equals x. Remember that the logarithm and the exponential with the same base are inverses. So we have e to the 1.875 equals, and then since those are inverses, you're going to be left with whatever the argument up here in the logarithm is. So x plus 1.5, and then we subtract 1.5. So if we subtract 1.5 from both sides, e to the 1.875 minus 1.5 is approximately 5. And I went ahead and put this up on the graph. So I have 2 natural log of x plus 1.5. And so at birth here, so when time is 0, we got the length is 0.8 approximately. Then we said, okay, well, what if we want the output to be 3.75? So let me just put 3.75 up on the graph here. So I just typed in y equals 3.75, and let's see what that ordered pair would be. So at around x, at about x equals 5, we get the output of 3.75. So we can just take a look at the graph, and mathematically, we are solving that equation and using that model to answer some questions. So that's a little bit of applications on logarithms and the change of base theorem, common log, and natural log for 4.4.